Hello. Good morning, everyone. Welcome to the first CAiRE Center for AI Research webinar on artificial intelligence. We're very honored to have Professor Yann LeCun from NYU and Facebook AI to be our inaugural webinar speaker today. We're going to have a virtual fireside chat with him. This is for my class, 4230, Deep Learning on and NLP, but also we welcome other HKUST faculty and students, as well as some students and faculty from other universities. So we have about 200 audience today. And so we will start the webinar and then I will be hosting it. I'm Professor Pascale Fung from CAiRE, and I will be asking Yann some questions, and he will present his view on the past, present, and future of deep learning and AI. And at the end, we will have about 20 minutes of Q&A. You can send your questions via a Q&A session. It's going to be via chat, and Professor LeCun will answer your questions. So first, let me start by introducing Professor Yann LeCun. I think I don't really have to do much of introduction. Then you all know him. He's like the superstar of AI. He is the 2018 Turing Award laureate, together with two other researchers, Yoshua Bengio and Jeffrey Hinton. He was awarded for conceptual and engineering breakthroughs that have made deep neural networks a critical component of computing. He is also a member of the National Academy of Engineering and Chevalier de la Légion d'honneur, that is the knighthood bestowed by the French government. And his background, other than being the VP and Chief AI Scientist of Facebook and Silver Professor at NYU, he is the founding director of Facebook AI Research and of the NYU Center for Data Science. He has engineering diploma from ESIE in Paris and a PhD from the Sorbonne University in France. He joined AT&T Bell Labs in 1988 and AT&T Labs in 1996 as head of image processing research. So let's welcome Professor LeCun. My first question, actually, Yann. So you were at Bell Labs in the late 80s, early 90s. I was also
like you.
Yeah.
You were there too.
Yes, I was there too, but unfortunately we didn't meet then. But so you were heading image processing, I was doing NLP. So can you tell us about so your work, how it started then? You invented LeNet, I remember, with your colleagues at Bell Labs at the time. And that was basically the beginning of convolutional neural net. Can you tell us a little bit about how it all started, your experience, and so on?
So I have a story to tell you, which is that I gave my first talk in English at a workshop in France in 1985. And it was a workshop that was in the French mountains in a center maintained by NATO. And there was a bunch of very famous people in that workshop. And I was a young student. I was in my second year of PhD. And it was like, people like John Hopfield, and these may be names that you don't know because they're kind of from a foregone era. There was Terry Sanowski, who's still very well known. At the time, he had just published a paper with Jeffrey Hinton on Boltzmann machines. And a whole bunch of like very sort of seniors, famous people, were giving talks, and I was supposed to give a talk, and it was my first talk in English. My English was terrible at the time. I was absolutely terrified. And there was a bunch of people in the room who, there was a guy in particular. He looked like a cowboy from Arizona. He had, sideburns and cowboy boots and everything. And every time someone was giving a talk, even a very senior person, this guy was very young, just out of PhD, he would ask a very nasty question, would basically bring down the entire talk. And he would do this to everyone in the room, regardless of seniority. And to me, as a French person, and I'm sure you can relate to this coming from Asia, this was completely unthinkable, right? You would not kind of question, a talk by a very reputable person if you were just a young person coming out of PhD. So I thought that was incredible. So I asked my friends who were with me at this workshop, who are these guys? And my friend told me, oh, these guys, they're from Bell Labs. They're incredibly arrogant. When you're at Bell Labs and you hear someone give a talk, you tell them it's been done at Bell Labs 10 years ago and it doesn't work. And so that was my picture of Bell Labs.
Yes, I remember.
So then I talked to these guys. They were actually very nice. And I talked to these guys from Bell Labs at this workshop. And apparently I impressed them because 2 years later, I went to the US to give it, to go to a summer school. Actually, it was 1 year later. And they knew I was in the US and they invited me to give a talk. And then they kind of remembered me after I finished my postdoc. And that's when they kind of went after me and tried to hire me. So this is to tell you that, so one other story is that when I gave my talk, I was absolutely terrified by this guy who was asking nasty questions. And I give my talk, nobody understands a word I was saying because my English was so bad. And this guy, raised his hand to ask a question. And I literally liquefied. I was terrified of this guy because, he was asking those such nasty questions. So I literally liquefied in place because I was so scared of what he was going to ask. And he said something nice. And so that's how I got hired at Bell Labs, essentially. 2 years later. Now at Bell Labs, it was really incredible because I was invited to visit the lab when I interviewed, and I was taken around various labs that were part of the same organization that I was supposed to work in, and they showed me all those labs, and I'd read about the work that was taking place in all of those labs in magazines like Scientific American. Everything that people were doing in those labs was basically famous. In fact, one of the labs I visited was Arthur Ashkin's lab, who was working on, it was a physics lab, and he was working on slowing down atoms using laser molasses. He won the Nobel Prize a couple of years ago. He actually lives in my town. He's just a mile away from here. In New Jersey. So I was incredibly impressed. So I could not refuse an offer from Bell Labs. I mean, I don't know what you felt about, how you felt about it.
Yeah. For
Pascale,
me, it was a dream as a student to go to Bell Labs, and I finally got there. It was a dream.
That's right. I mean, I didn't know about it that much before I kind of, really got here. Of course, I learned about the history, all the technology of the modern world basically was invented at Bell Labs, and things we use every day, things everybody uses every day, like, Unix and C and C++, yes. But also going back, more than that, solar cells and laser and things like that. So transistor, right? Mm-hmm. So that was an incredible time. And you have to realize that, so I joined Bell Labs in October 1988. And then at the end of 1989, Vladimir Vapnik also joined our group, the same lab I was in. So Vladimir Vapnik at the time was a Russian mathematician who wanted to move to the US. And some of you may have heard his name. He's the co-inventor with Isabelle Guillon and Bernard Boser of the support vector machine and kernel machines. And he kind of wrote the sort of basic theory of basically the theory of learning, if you want, like statistical learning theory, the so-called VC theory of learning. I was working on convolutional nets, and a couple of offices down from mine, they were working on support vector machines. So support vector machines, which was the dominant method in the late 90s of machine learning, and convolutional nets were invented about 2 years apart from each other and 2 offices apart from each other. That part of the building, that building where that used to belong to Bell Labs was eventually abandoned and stayed abandoned for 10 years. And now it's been kind of refurbished, if you want. And now the people who are in the same location in that building is actually friends of ours that used to be colleagues at Bell Labs, and now they work on deep learning research for autonomous driving, and they are part of NVIDIA. So
Oh,
that's an incredible story.
that is incredible. That is incredible. So I personally, my first paper presentation at the conference was a Euro speech. And as a student, I was also challenged by a guy from DARPA, actually, George Doddington. And I was shocked as well. But that was a very good experience of being challenged as a student. In fact, I remember your first paper, or one of the first papers on the CNN was not accepted by CVPR initially. Can you tell us that story?
Well, so that was the second wave. The first papers on convolutional nets, go back to the late 80s. In fact, when I was at Bell Labs, the first paper was kind of obscure, but the paper that really sort of was the first nice paper, if you want, about convolutional net was published in Neural Computation in early 1989. So, that's a long time ago. That's over 30 years ago. And then there was a follow-up paper at NIPS. It wasn't called NeurIPS yet, in late 1989, which was published in 1990. So these were the first papers on convolutional nets. And at the time, it actually made a relatively big splash. The machine learning community was relatively small. The neural net community was relatively small. NIPS had maybe 400 or 500 participants or something like that. So it wasn't like it is today. But that paper actually, I think, had an impact. But then what happened is that in the mid-90s, neural nets fell out of favor. So people kind of lost interest in those methods for various reasons that we might talk about later. And then we, in the early 2000s, Jeff Hinton, Yoshua Benju, and I kind of tried to revive the interest of the community in those methods. I call this the deep learning conspiracy, but it's a bit of a joke. And I started publishing papers on convolutional nets again around 2003. And then by the end of the 2000s, it was kind of working pretty well. And so we started having really good results on something, applications like semantic segmentation and things like that. And so we submitted a paper at CVPR, which was CVPR 2012. So this was submitted at the end of 2011, where we had a system that could do semantic segmentation, which means labeling every pixel in an image with the category of the object it belongs to. And that system had better accuracy than the best competing system and was 50 times faster running on the same hardware. But also we had specialized hardware that was making it even faster than that. We were pretty sure the paper was going to be accepted, but instead it was rejected by all three reviewers. And the reviews were pretty much along the lines of, we can't believe a method that we never heard of could be so good, so there must be a mistake. So this was late 2011, and most young people in computer vision had never heard of convolutional nets or didn't believe it was working. So this was double-blind review. I did not know how to respond to the reviewers in a way that would kind of change their mind. So I just wrote a letter to the program chair saying, I think it's, I understand that you're not responsible for the decision. I had been program chair of CVPR 5 years earlier, so I knew that he had nothing to do with it. But I told him, I don't think it's worth submitting papers that are about neural nets and machine learning to computer vision conferences because people just don't understand it. So I'm going to tell my students not to submit papers to CVPR anymore, and you can publish my letter. And so he published my letter, but he anonymized it. So he removed the names. But of course, everybody knew who it was.
Oh.
It was a bit of a joke. It changed very quickly because by the end of 2012, our friends at University of Toronto kind of beat the record on ImageNet using convolutional nets on GPUs. And then by 2013, everybody in computer vision was really excited about convolutional nets. And by 2014, everybody was working on it. And by 2015, you couldn't get a paper accepted as CVPR unless you use convolutional nets.
Yeah. So
in the space of 3 years, things changed completely from one extreme of the spectrum to the other extreme.
Mm-hmm. Yeah. So yeah, so for a lot of the students working on their thesis right now, right? And I remember even when I was at the labs and many other labs I worked at, there was always this one young guy or woman working on neural net, but their results were not beating our results using other statistical methods, but they carry it on. I think so that persistence. So what gave you the drive to and the what gave you this confidence and drive to continue working on neural network when over so many years at a time when there was no approval from the larger community and all that?
I mean, I think you have to be kind of a pragmatic scientist about it. So there are two things, right? There is, these beliefs, first of all. Then there is empirical results. And, sometimes your belief you have to believe in something even if the results are not there to kind of keep working on something. But in the case of convolutional nets, the results were there. There are a number of applications where the results were significantly better than every competing method. I think what was more surprising was that those results were not considered important or not, or kind of ignored by the community. So convolutional nets were the best known method for doing things like obviously recognizing characters, but also detecting faces, also recognizing road signs and detecting pedestrians, and a number of and semantic segmentation, as I explained. But people in sort of the mainstream computer vision were kind of dismissing those results as flukes, essentially saying, oh yeah, I mean, they're slightly better, but we can catch up with more traditional methods. Or, we don't really believe that those things can work or whatever. Maybe there's a mistake in your experiments, or, I mean, there is a lot of excuse you can tell yourself to kind of convince yourself that this is not the case. But, I knew those results were good. And so, I knew that the potential was great. And what was limiting the performance of the systems at the time was the size of the data sets. The data sets at the time in computer vision in particular were very small. And so ImageNet changed everything because it was the first data set that not only had over 1 million training samples, but also it had many categories. And it turns out for supervised learning to work well, for convolutional nets and things like that to work well, you need many categories. It works better if you have more categories than if you have few categories.
Yes.
So if you do things like pedestrian detection or face detection, you only have 2 categories, and that's actually not an ideal situation for convolutional nets. Now, there was something else, so that was kind of disappointing, and this is more connected with your interest, Pascale, which is speech recognition. So there was quite a few people in the 90s, early 90s, who were working on speech recognition using neural nets. Among them, Léon Bottou, Patrick Hafner, Yoshua Bengio did his PhD on this, and a bunch of other people. And then people like Hervé Bourlard, who's director of NRI Lab in Switzerland now, and Chris Wedekens, who he was working with at Philips at the time. And then people in Cambridge also had good results using neural nets. But those results using neural nets for speech recognition were not quite, superior, if you want, to kind of approaches that were using a mixture of hidden Markov models and mixture of Gaussians. They were good, they were fast, but they were not, record beating. And so people kind of abandoned this in the mid-90s. It kind of died out also at the same time as neural nets were abandoned for other applications. And it's only in the late 2000, 2008 roughly that people kind of came back to this, because results starting to get really good using recurrent nets, for example, for kind of relatively simple data sets like TIMIT. And so Jeff Hinton did something very smart. He had 3 students, and he sent those 3 students to do internships in the three companies that had the best speech recognition engines at the time, which was Google, Microsoft, and IBM, with the instruction to just replace one small piece of the acoustic modeling system by a neural net, keeping everything else the same. So just compare, do an A/B comparison, replace mixture of Gaussian models for acoustic modeling by neural nets. And all three of them got good results, basically beat the mixture of Gaussian models. So all of a sudden, IBM, Google, and Microsoft got really interested in deep learning. And two things came out of it. The first thing that came out is that about a year later, a common paper came out that was written by all three teams, which is completely unheard of. But also within 18 months, every single speech recognition system on smartphones was using deep neural nets. So this went from basically, academic research lab result to being in the hands of hundreds of millions of users in the space of 18 months. And that was incredible. And it happened earlier than the sort of ImageNet revolution that really kind of captured the attention of everyone. So speech recognition, the deep learning revolution in speech recognition happened about a year and a half before the deep learning revolution in computer vision, which itself happened 3 or 4 years before the NLP revolution.
Yeah. In fact, I remember all this because I'm in both NLP and the speech community. And I also remember when Joshua published his first paper on neural language modeling. I think it was 2000, like early 2000, right? And I remember people were talking about this, okay, another, paper that's trying to beat n-grams, statistical n-grams. And I remember his system did not beat n-grams. And people were, again, being dismissive, saying that, there's yet another attempt, nobody has beat n-gram in 30 years. I remember the sort of the inventor of n-gram, right? Statistical language modeling was Fred Jelinek. And I remember him saying, we want to do something different, but nothing beats statistical n-gram. I remember I still hear his accent. It did not beat statistical n-gram for the longest time until 2010-ish. And when recurrent neural network came out, then it got rid of the n window constraint, right? So you can actually go get the long distance dependency between words, and that was truly a revolution. And I remember also that what's astounding is that given I was at Bell Labs also in the 90s and all, I had never seen the deployment speed, like sort of a technology transfer speed from a research lab to the market as fast as after all this deep learning methods came out.
Yeah,
I think. Yeah, so, and all the speed at which all the applications, basically almost all AI applications, I would say, have basically benefited to have a jump in performance by using one form or another of the deep learning technology, right, and architecture. And that's just astounding. And it's the first time in my life I also see that the market is driving research in a way. It used to be, when we were at Bell Labs, we would be doing some research nobody has heard about, and they wouldn't even know until like maybe 10 years later, right? And now it's a lot of times the market is driving and say, can we use deep learning for this and that? And you know what? A lot of times you can, and it has given us a lot of new research challenges. Yeah. So I would also like to ask you about a little bit about, so we talked about the past. So maybe touch upon the present and more importantly, the future. So where do you see the challenges lie for, deep learning research in particular, but AI research in general? What should people work on today? What should people pay attention to? And or maybe also 5 years from now or even 10 years from now. I'm sure people ask you this question a lot, but since our audience is very technical, you can also give us a bit more of a theoretical background if you want.
Sure. So I see three main challenges for the future in AI in general, in machine learning in particular, and deep learning more specifically. The first challenge, I think, is the fact that we know how to, train machines to do perception, essentially, right? So to do computer vision, speech recognition, and it's, basically it's a feed-forward process, right? So we feed an input to a neural net, we run the neural net for a few layers, maybe 50 layers or so, and then we get an answer. So that's kind of feed-forward perception. But the question is, like, how do we get machines to reason? Well, how do we train a machine to reason? So to kind of solve problems where the answer does not come after just 50 steps of computation, but basically involves kind of long chains of reasoning, if you want.
Mm-hmm.
So that would be the first challenge, and I might speak to perhaps a few potential solutions to that problem later.
Mm-hmm.
The second one is how do we move away from supervision? So how do we move away from having to train a machine by associating inputs and outputs and requiring millions of examples for any task that we wanted to do? And my statement is also applies to reinforcement learning. So reinforcement learning is not a solution to that problem. The main issue I see here is that when we train a machine to perform a task supervised, we ask the machine to predict a relatively small amount of information, right? So if we train on ImageNet, for example, what we're asking the machine to predict is a class among 1,000, so it's roughly 10 bits of information. And we are supervising the machine by giving it 10 bits of information for every sample. Okay, it's not a lot of information that we give to the machine for every sample. In reinforcement learning, it's even worse because when the machine produces an answer, we don't tell it what the correct answer is. We only tell it whether the answer it produced is good or bad. And so it's less information than in the context of supervised learning. Sometimes it's information that we don't have to provide ourselves. It's the machine can compute this value itself, or the environment gives it to it. But it's very expensive because we have to interrogate the environment to get the reward back. And so it's not really practical in the real world. There's very, very few applications of reinforcement learning in the real world. The only application of reinforcement learning in the real world are applications where you have an incredibly large amount of data. So for example, click data, right? You want to learn if you want to show, this ad or that ad to someone, is the person more likely to click to this particular advertising than to this one? And so there you can do many trials because there are billions of users. But that's kind of an exception. If you want to train a car to drive itself, you can't use reinforcement learning. It would just take too long. Okay. So that's the problem. And the problem is very immediate for a lot of situations. If you are a social network or a search engine, if you're Facebook or Google or Microsoft or whatever, you'd like to be able to translate any language into any other language. And we don't have parallel text for all languages. So for most languages, we don't actually have a lot of text. And so we can't really just train a machine supervised to translate, Swahili into Urdu or something. Or some, obscure dialect of, Eastern China into, some dialect of Northern Afghanistan, right? We're just not going to have the data. So we're not going to have enough data to in supervised mode, to train a machine to know how the world works, to learn about physics, right? To know that by default, when you drive a car and you're driving a car next to a cliff, and you turn your wheel to the right. In Hong Kong, do you drive on the left or the right?
We would drive in the British way.
On the left, okay.
On the left.
So you're on a cliff and the cliff is on the left side. Okay, yeah. You're driving on the left. If you know that if you turn the wheel to the left, the car will, drive off the cliff and fall.
Yes.
Because you have an intuitive physics, a notion of intuitive physics, right? But a machine learning system that learns from scratch has no idea that this is the case. It will have to actually turn the wheel and watch the car crash and do this multiple times, probably thousands of times before it understands it's a bad idea. And then it will have to do it another few thousand times before it realizes how not to do it. So, you know, what allows us to learn quickly is that we've learned somehow a model of the world that allows us to make those kinds of predictions. And nobody supervised us to do this. We learned this as babies when we were, you know, a few months old. Gravity, actually, we learn around the age of 9 months. Okay, we don't learn this earlier. So babies who are 6 months old, if you show them an object that appears to float in the air, they're not surprised. Babies who are 10 months old, but you know, in the meantime, they've learned about gravity. You show them an object that floats in the air, they look at it and they open their eye and they are very, very surprised because they know that objects are supposed to fall. So we only learn this by observation mostly after a few months of life. And the question is, what type of learning paradigm do humans and animals use to learn this kind of knowledge, background knowledge about the world? I think, personally, I think this is the kind of learning that allows us to, you know, elaborate some sort of common sense, right? Common sense comes from the accumulation of enormous amounts of background knowledge about how the world works. And we learn this by observation. We do not know how to do this with machines yet. So that's the two main problems: reasoning, learning to reason, learning without supervision, essentially learning how the world works just by observation without having it linked to a task, if you want. And then the third problem, for which I have absolutely no idea how to approach it, is sort of learning to represent sequences of actions in a hierarchical way. So with convolutional nets, the advantage of convolutional net is that we can learn, we can train the machine to learn to represent the world in a hierarchical way, right? It starts with pixels, and the first layer of convolutional net sort of detects very simple features like oriented contours and things like this. And then the second layer assembles those detected contours into little motifs like corners and crosses and things like this. And then the next layer up kind of, you know, detects combinations of those into parts of objects, and then you have objects and then scenes, etc. So you have this sort of compositional hierarchy that represents the world from sort of the low level to the high level. But there's a similar hierarchy for action plans. So if I tell you, you have to go to, you can do this today, but if I tell you have to go from Hong Kong to New York, you know that you have to go to the airport, fly an airplane, and then you get to the airport in New York and catch a taxi or something. Now to go from wherever you are to the airport, you have to, you know, catch a taxi or take the subway or the bus or whatever, the train, and then go to the airport. Now to get out of your building, you have to stand up, walk out to the door, open the door, you know, remember where, you know, how to kind of get out of the building, etc. And so you have this sort of hierarchy of decomposing a complex action into sequences of simpler action, lower level actions. And then those actions are not completely defined because their particular instantiation will depend on the particular configuration. Like to get out of your room, you have to know where the door is, and maybe some obstacles have moved, so you have to kind of work around the obstacles. It's not completely determined by the plan. And so the big question, I think, is how do we devise architectures and learning paradigms so that we can build a hierarchical system that will learn to represent complex action plans in a hierarchical way? And nobody has any idea how to do this. I sure don't. Maybe some people do, but I don't. But I think it's a really crucial problem. Right, so these are the problems. I haven't talked about solutions.
Yeah, so basically you're talking about so the reasoning part, the common sense part, and actually the last part sounds like it's a planning, right? What in AI is traditionally called planning. And people have been working on these problems for decades, like really 3 very important challenges for AI. I myself in NLP and speech, I feel like we actually sort of so far have been working on the low hanging fruit, meaning that we basically circumvent these problems. We like oh, we're not trying to do reasoning. We just kind of do, in question answering systems, we're just trying to imitate input output. Like we're just trying to force an output. Machine translation is the same. We don't do planning at all. We don't do, common sense or any of that. We just try to do input output so far. So far we've been kind of lucky to have being able to avoid these things. And then once the low hanging fruit are gone, like, right, we have to face the music, right? So to speak,
Yeah.
all these three big challenges. Now, can you now elaborate a little bit? You said that you might be able to tell us a bit about, the potential solutions you're working on, or?
Right. Okay, so there's one thing I'm not working on myself, but other people are, but I'm really interested in, which is this idea of reasoning, kind of allowing learning machines to reason as opposed to just, computing feed-forward answers. There's sort of two approaches to this. One approach is to think of the computation. So this is something that was proposed by Léon Bottou in a kind of forward-looking paper that was published, I think, in the Machine Learning Journal about 10 years ago.
Would you like to share your screen or with slides or something? You can, if you want to.
Sure. Yeah. I don't have anything to show, but I might in a minute.
Okay.
So the idea there is that you have some sort of recurrent net, and this recurrent net kind of works with a working memory, right? So there's a working memory that basically contains all the facts that you know about the world, perhaps. You can think of this as kind of some sort of associative memory that you can access through a key, and it gives you a value. And if you want this memory to be part of a neural net, it has to be a differentiable memory, right? So this idea was proposed a while ago by people at Facebook, actually, Antoine Borde and his collaborators, and it's called memory networks. You might have heard about this. There's also the end-to-end memory networks. There was a kind of somewhat similar work at DeepMind called the Neural Turing Machine, also based on having a differentiable memory. And this constitutes the basis of the sort of recent revolution in natural language processing that uses transformer networks. Transformer networks are basically neural nets where every group of neuron is one of those kind of memory network type architecture. You can think of it this way. So the idea there to kind of allow machines to reason is that you have a recurrent neural net, and this neural net produces an address, a key, if you want, for a memory, and accesses a fact from that memory, gets the result back, and then kind of works on this, and then accesses the memory again. And so it keeps reading and writing, reading from this memory and writing into it. And you can think of an inference engine in sort of classical AI as being something of this type. You have, you have a knowledge base that contains facts. You have rules, which you can think of as being implementable by a neural net. And then you look for a combination of facts that satisfy a rule. You apply the rule, and then you add the new fact into the knowledge base. So you can think of that as a process of reasoning, and you could very well implement this by completely differentiable modules, where they have this differentiable memory, and then the engine that produces new facts is itself a neural net that is differentiable. So that's one approach to reasoning. Another one is reasoning by energy minimization, I would say. Okay, so if you think about the type of reasoning that takes place in a Bayesian network or a graphical model, in the sort of the probabilistic reasoning tradition, it's basically constraint satisfaction. So you have a graph that represents your knowledge about the world, and this graph essentially imposes constraints on subsets of variables. And so what happens now is that you clamp the value of some of the nodes in the graph that correspond to observed facts about the world. And then what the system needs to do is find a combination of the other variables, of values of the other variables, that is consistent with the ones that you observed. And consistent means that it maximizes some probability or it minimizes some sort of energy, which is the same, it's completely equivalent. You can do either. Okay. So that's the basic idea of for example, what's called a factor graph, which is a particular type of graphical model. Okay, so essentially in this context, reasoning comes down to finding a bunch of the value of a bunch of variables that minimize some energy, or satisfy some constraints, which is really the same thing. And that we kind of know how to do. It's just that it's not been really widely applied, I think, for too many things. But I've been working on this, so I call this energy-based models in the a particular form of this. And the question is how you train those machines so that it gives low energy to combinations of variables that are good, and higher energy to combinations that are not good. So that's for reasoning. And then the other topic, which is I think I'm sort of more actively working on, is the problem of reducing supervision. So I've been advocating the idea of self-supervised learning, which is essentially the idea of training a machine to predict parts of its inputs from another part of the input. So a concrete example is something that Pascale, you just mentioned, which is language modeling, right? So I give you a sentence or a sequence of words, and I remove some of the words, okay? Maybe the last word only in the sequence, or maybe a few words in the middle. And then I train a neural net to predict the words that are missing, okay? So that's an example of self-supervised learning in the sense that it's trained to fill in the blanks, right? In the context of natural language processing, this type of learning has been unbelievably successful. So there's been a kind of a second deep learning revolution in NLP that occurred about a year and a half ago in October 2018, when Google published a paper on archive on basically the whole idea of BERT, okay? So BERT is exactly this idea that you take a sequence of words, you remove some of the words, then you train one of those transformer networks, which also had been proposed by another team from Google. And you train it to predict the words that are missing. And so, this draws on previous work on, very similar work to learn representation of text. There was, I think it started with Yoshua's work on neural language models, which was largely ignored. But there was some more recent work by Ronan Colbert and Jason Weston about 12 years ago or so, around 2009, 2010. And they had a very provocative title in their paper. They put out a paper whose title was Natural Language Processing Almost from Scratch, okay? And this paper absolutely infuriated the natural language processing community. I don't know what you thought about that paper, Pascale, but I know the reaction for some people in the NLP community who were absolutely furious by this paper, partly because the paper was not sort of respecting some of the rules of how you kind of measure performance of systems, etc. They've sort of cut some corner there. Eventually they fixed that, but it was basically breaking every assumption that every researcher in NLP had been kind of working on for the 20 years before that. And essentially the way they pre-trained their model was that they had a neural net that looked very much like a convolutional net, which had a single scalar output, and that neural net would be pre-trained unsupervised by showing it a sequence of words from a corpus, and then training the system to give a high score to that sequence of words because it comes from real text. And then it would randomly substitute the middle word or some subset of words, and then train the same neural net to produce a low score. So basically, think of it as a discriminator, right? It's supposed to give high score to kind of well-formed sentences from the corpus, and then bad scores to kind of corrupted sentences. Okay, that's what I call an energy-based model. And with this technique, they were able to train a system to learn sort of vector representations of text that were surprisingly good. And then Tomasz Mikołaj had the idea of simplifying this idea a lot, and then just using essentially lookup tables and linear model with word2vec, right? That was word2vec, and that took the field by storm. That was in the around 2012 or 13 or something.
Yes.
And then there was fast text, and there was like a whole bunch of improvement on this. And then transformer networks and BERT and various other variations of this, where people kind of use this idea, right? So this has caused a revolution in NLP, because when you pre-train a neural net to learn representations of text using this kind of self-supervised learning by filling the blanks, you get really, really good representations. You can train them to learn representations of text independently of language. And then if you use those representations, you don't need as much data to then train the system for a supervised task like sentiment analysis or translation or summarization or parsing or whatever. So that, or natural language inference. So that made a huge difference. Now, very naturally, people thought, why don't we do this for vision? Can't we use self-supervised learning for computer vision? And I've been working on this since quite a long time, but one paper I worked on in around 2014-15 was the idea that you should get a system to learn how the visual world works by doing video prediction, right? So give a system a few frames of a video and train it to predict what the next few frames in the video are going to be. If you use, so one natural idea is you take a convolutional net, spatial temporal convolutional net, feed it a few frames from a video, and then, have a few layers, and then have a decoder that's also a convolutional net that generates a prediction for the next frame or the next few frames. If you train that on video, it doesn't work very well. It produces blurry predictions. The images that are generated by the system are basically very, very sort of blurry, smooth images. And the reason is because the system has no way of predicting exactly what's going to happen in the video. And so the best thing you can do, because it's trained with least square or something like that, is to predict an average of all the possible things that could happen, right? So you're looking at me right now, talking, and in a second, I could move my head to the left or to the right, to my left or to my right, opposite for you. And you probably can't tell in which direction I'm going to move. And so if you have to make a guess, a single guess, to minimize the squared error between your prediction and a frame of this video a second from now, the best thing you can do is predict the average of me on the left and me on the right. And that's a blurry image of me, okay? So that's not a good prediction. So the question that we need to solve there to kind of train a system like this to make predictions is how do you train a system to make predictions knowing that there are multiple correct predictions and you never know which one is going to happen, okay? So it's the problem of prediction under uncertainty. So if you are in the discrete world, you're trying to predict the next word in a text, or you're trying to predict a missing word in a text, as is the case for BERT, as I was talking about earlier. It's not a problem because you can produce a probability distribution over all possible words, okay? You give a score for every word, you pass those score through an exponential and you normalize the exponential. This is what we call a softmax, right? Yeah. What you get is a bunch of numbers between 0 and 1 that sum to 1. You can train this with cross entropy. What you get is a good best estimation for a probability distribution over the missing words. You can't do this for video frames. We do not have a softmax over all possible video frames because it's a high-dimensional continuous signal. And in fact, we have no idea how to represent kind of meaningful distributions over video frames, at least not in any convenient way. And so that's the main technical issue we need to solve, which is how do you represent something perhaps weaker than a distribution over high-dimensional continuous spaces like video frames or like image patches. And there's no good solutions to this. But one possible approach, there's two possible approaches. And maybe I should draw a picture. Okay, yeah, so I'm not going to use slides. I'm going to draw on a whiteboard. Okay, can you see my screen?
Yeah.
All right. Okay, so here's the problem. So let me give you a very simple example where I have two variables, y1, y2, and I have training samples, and my training samples are something like this. Okay, these are my training samples. And I want a system that captures the dependency between Y1 and Y2. Okay, so obviously I cannot just have a function that predicts Y1 from Y2 or Y2 from Y1, because for every value of Y1, there might be multiple values of Y2 that are correct. So if I just have a neural net to which I feed Y1, and it produces a prediction for Y2, okay, and I train it by minimizing some cost, basically in supervised mode, okay? So in my representation here, a square box is a cost, okay? And one of those kind of rounded box is a deterministic function, let's say a neural net, okay? So if I build a system like this, which is kind of the standard model for supervised learning, this is not going to work because, you know, if I give you this value of Y1, there is 2 possible values for Y2, and this neural net can only produce 1. So this is not going to work. So what I'm going to use is I'm going to use implicit functions, okay? Basically, I'm going to build a function f of y being the vector Y1, Y2, okay? And this function is going to take y, the vector y, so all the values. And this function is going to tell me, is going to give me a low value if y, the vector y, looks like it's similar to points in the training set, and higher value it's if higher values if it's different. Okay, so basically, what I want is I want this f function to take low values on the manifold of data and higher values outside. Okay, so now I'm drawing the lines of equal energy, if you want. So I call this function an energy function. Okay, so we get low energies here near the data points and higher energies outside. That's called an energy-based model. Now, what am I going to put in that box? That's the first question. And the second question is, how am I going to train it? All right. And for the training question, there is basically 2 classes of methods. The first class of methods is called contrastive methods. And the second class of method, I call them architectural. So contrastive methods basically are based on the idea that you're going to take a data point. So you have a training set, right? Your training set is, you know, Y1, I shouldn't call it this way. Y1, Y2, Y3, etc., YP, right? That's my training set. And what I want is I want to give low energy to my training set. I want to train my system so that it gives low energy to the training set. But I also need to train it so it gives high energy to anything that is not the training set. Okay. So a technique consists in taking a sample, okay, Y1, so let's say it's here, and then taking what's called a contrastive sample, and I'll call it Y bar, let's say here, okay. And then what I'm going to do is I'm going to push down, I'm going to change the parameter of my energy function so that the energy of the blue point goes down and the energy of the pink point goes up. Okay, so if I keep doing this with blue points that are on the data manifold and pink points that are outside, then the energy function is going to take the right shape. It's going to have lower energy for data points than for anything else. And if I have a function like this, then I can do inference. If I give you a value of Y1, I should use the same color. If I give you this value for Y1, I can predict that the correct value for Y2 is either here or here, because those are the 2 values that minimize the energy as a function of Y2 for that given Y1. So I can do inference, right? I can infer what the good values of Y2 are from the value of Y1 if I have this energy function. Now, if you are kind of probabilistically minded, you immediately think, well, this energy function is kind of like the negative log of a probability distribution. Yes, except it's not normalized. I don't need to normalize it. And that's really the important thing, because normalizing complex probability distribution is usually fraught with computational intractability. So here we're just not normalizing anything. Okay, we're just manipulating the energy function directly. So those are contrastive methods. There is one domain in which contrastive methods have been incredibly successful. And you can think of BERT as a type of contrastive method. So BERT basically is a particular example of this, where you take a sample Y, you corrupt it by masking some words, for example. So you get, some other corrupted version of Y, which I'm going to call X. Then you run X through an autoencoder or some sort of neural net. Doesn't matter what it is. And then this is going to try to reconstruct Y, and you measure the distance between the reconstruction and the uncorrupted initial input. This is called a denoising autoencoder. Okay, the special case for BERT is actually called a masked autoencoder, but this is a special case of denoising autoencoder. This was the idea of denoising autoencoder was proposed by Pascale Vincent in Montreal. It was actually based on an idea that I talked about during that talk where I was terrified in 1985. But and in fact, you can think of this as an energy-based model where you take a point Y, you corrupt it in some way. Okay, so this is the corruption. You get a corrupted point now. And now you train your network to map the corrupted point back to Y. And what that means is that if you give this corrupted point to your network, it's going to reconstruct the uncorrupted point, which means the reconstruction energy is going to be equal to the square distance between those 2 points. And so indirectly, it's a way of training the energy function to be large outside the manifold of data. Okay, so it's basically an energy-based model. So there's another very recent success of contrastive methods in the context of image recognition. And it's based on the idea of what's called Siamese networks. So Siamese networks are basically you give, it's a bit of the same idea. You give an X and a Y, and which may be distorted version of each other. You give those two to the same neural net, the same convolutional net if it's an image. Okay, so those two networks are two identical copies of the same network that share the same weights. And you compare the outputs, okay, with some cost function, say a cosine distance or something like that. And then the way you train the system is the energy of that system given a pair XY is the reconstruction, is the cost on the output, okay? And you train it with two different sets of samples. One set of sample is where X is an image and Y is a slightly distorted version of that image. So those two images are basically the same. They are identical. And you train the system to produce a low cost on the output. So you basically train the system in such a way that the outputs of those two copies of the neural net are identical. Okay? So that's the positive phase. This is like training the system to give low energy for training samples. And then you generate contrastive samples by feeding an image X. And then for Y, you take an image that you know is different. You know it's a completely different image, had nothing to do with X. And then you train the two outputs to be different. Okay, so you train the energy to be large, basically. And this is very much, you know, in the same spirit as what I was explaining earlier, that you have data points on the manifold. Those are X and distorted X. And then you have points outside. Those are X and non-X, if you want. And you push down the energy of X and distorted X, and you push up the energy of X and non-X. Okay. This is called a Siamese network. And I had kind of one of the first papers on this in around 1993. There was earlier similar ideas by Jeff Hinton and Sue Becker using sort of different criteria. And those techniques kind of, I tried to revive them in the mid 2000s with two of my students. But they didn't pick up a lot of interest, except in very recent months, because 3 different teams, 2 at Facebook and 1 at Google, use this kind of technique to pre-train convolutional nets for computer vision. So they used very large data sets, either sort of large ImageNet or ImageNet plus data augmentation or some other data set. And so what you do is you take an image from ImageNet, you take another image and you distort it in some ways. You train the 2 networks to produce this identical outputs, essentially. Then you take one image from ImageNet and another image from ImageNet that you know is from a different category. And then you train the outputs to be different. And one paper is called MOCO, and it's that's called, well, the MO is momentum. I can't remember what the CO stands for. This is by Kai-Ming He from Facebook AI Research. It's the same guy who invented ResNet, which I'm sure many of you know. The second technique is called PEARL. That means pretext invariant representation learning. That project was led by Ishan Misra, who is a young research scientist at Facebook in New York. And then the last paper, which has very good results, is called SimCLR, SIMCLR. And that is by a large team of researchers at Google. The last author is Jeffrey Hinton. And the reason why they get good results is because they train, for an enormous amount of time on lots of TPUs or whatever. And so those 3 techniques use this, and those are the only 3 papers that I know of that use self-supervised learning in a convincing way to learn features that can then be used in a downstream supervised task and basically reduce the amount of supervision you need to reach good performance, record-breaking performance. So that's recent progress. In my opinion, though, those methods are kind of running into a wall. And the SimCLR paper actually made that pretty obvious in the sense that the amount of computation that's required is absolutely gigantic. And the reason is that those methods don't scale very well, because if you need to push down and push up on energies, the dimension of the space is so large that there's too many places where you need to push up the energy. You're just never going to be able to shape the energy function in the right shape because the dimension of the space is too large. So I'm much more fond of architectural methods. Unfortunately, they don't work as well right now. So the architectural methods are based on the following idea. And stop me whenever you want, Pascale, because I'm kind of rambling right now, okay?
It's okay.
So the idea is the following. You want to make a prediction. So I'm going to call the variables that I'm observing X, and then the variable I need to predict Y, okay? And I'm going to draw the same picture I drew before. You might have a training set of data points, and now I'm going to call this X, and I'm going to call this Y, okay? And for one given X, there might be multiple correct Ys. So if I'm using just a neural net to predict Y from X, it's not going to work again, because I can only make one prediction. I'm going to get those, I can only predict the average, okay? So what I'm going to do is I'm going to run this through a neural net, which I'm going to call a predictor. And that predictor is going to be an input to another neural net that I'm going to call a decoder. And this guy is going to make the prediction Y bar, which I can compare with the cost function with Y. Okay? But I'm going to make the Y bar the decoder also depend on an extra variable that I'm going to call Z. That's a latent variable. So you can imagine that if I have a set over which I can vary Z, so let's say in some space, let's say Z is 2-dimensional, I can vary it over some rectangle. Once this 2-dimensional Z goes through the decoder, it's going to generate some sort of 2-dimensional manifold in the output space. Okay, so the output space might have 1,000,000 dimensions for all I know. But if Z has 2 dimensions, then the output, as I vary Z in this 2-dimensional input, the output is going to vary, is going to basically describe vary over a 2-dimensional manifold embedded in this 1,000,000 dimensional output space. Okay, so now by changing the value of Z, I can make multiple predictions for Y bar. So this would be weaker than predicting a distribution over Y. what I can do is just predict a set, essentially, right? A manifold is like a set. So now, how do I train a system like this? The way I train a system like this is I give you an X and a Y. You find the Z that minimizes the energies. The energy is the C value, the reconstruction error. And then you make a step of gradient descent in the weights or the parameters of the predictor and the decoder, okay? So observe an X and a Y. First step you do is you minimize the energy function that depends on X, Y, Z with respect to Z. And we're going to call this an energy function that now only depends on X and Y. It doesn't depend on Z anymore. Okay? And the next thing you do is you know, there are parameters in the system, in the decoder and the encoder. You do W replaced by W minus some constant times the gradient of the energy with respect to W at this point, X, Y. Okay? Easy enough, right? So the part where you minimize the energy with respect to Z, oh, I'm sorry, I should have called this F, not E. Okay, so this is a new energy function, which physicists would call a free energy, but which is why I call it F. And it's obtained by eliminating one of the variables, the latent variables from the original energy. So in the little diagram I drew here on the side, the energy function of XYZ is equal to the cost function C applied to Y and to the decoding function that takes into account Z as well as the predictor function applied to X. Okay, and I'm running out of space. Okay, that's just a particular definition of E that corresponds to this architecture. All right, there's only one problem with this, which is that it doesn't actually work shown this way. And let me tell you why it doesn't work. Let me redraw the picture here. Okay, here is why it may not work. It may not work because let's imagine Z has the same dimension as Y. Then what's going to happen is that if I show you an X and a Y, you can always find a Z that will make the prediction error 0. Okay? Make the decoder the identity function, for example. Make it completely ignore X. Make it the identity function and make Z the same dimension as Y. Then for any X and Y, there's always going to be a Z that is going to make this prediction energy 0, exactly 0. And that's a bad model. It's a model that does not capture the dependency between X and Y because it gives 0 energy for everything. So what you want is a machine that gives low energy for stuff you train it on, but higher energy for things you don't train it on. And the solution to this is to limit the capacity of Z in terms of information capacity. You can do this through a regularizer, for example. Let me give you a concrete example. Okay, here is a energy function of YZ. And it's equal to Y minus a matrix multiplied by Z squared. And I put a constraint on Z such that Z is a one-hot vector. So one-hot vector is a vector with all zeros except one component is 1, okay? This energy function is the energy function of k-means, okay? I give you a vector Y. If you choose which Z vector among all the possible vectors that only have 1, 1 and all zeros, which one minimizes this energy? It is the one that selects the column of W that is closest to Y, okay? So the columns of W can be seen as prototypes in k-means. And minimizing with respect to Z corresponds to searching for the column of Z that is closest to Y, okay? And that's what vector quantization does. And you can train this with gradient descent and it works. Now, why does it work? Why, does it never produce a flat energy function like I was talking about earlier, is because the capacity, the information capacity of Z is limited. Z can only take k different values. If Z is a k-dimensional vector, it can only take k different values. Therefore, there's only k values in Y space that will have 0 reconstruction error. Okay, either Y is equal to one of the columns of W, in which case its reconstruction error is 0, or it's not, in which case the reconstruction error is equal to the square distance to the closest prototype. Okay, so the energy function there is the minimum of a bunch of quadratic balls. And because I only have k quadratic balls that I can place wherever I want, I never need to push up on the energy of anything, because by default, if I move one of those balls, the center of that ball is going to have low energy, but everything else is going to have higher energy. So this is what I call architectural method, because the shape of the energy function is defined by the architecture, and you never need to push up on the energy of anything, as in contrastive methods, because it's by construction. Okay. Here's another example. Another example is sparse coding, and some of you may have heard of this. Most of you probably haven't. It's basically the same energy function, except now I don't force Z to be one hot. Z is just a vector, but I regularize it like this. So basically, I tell the system, you should reconstruct Y by multiplying the Z vector with the matrix, but the Z vector needs to have a small L1 norm. So the term on the right is a regularizer that computes the sum of the absolute values of the components of Z, which is called the L1 norm. And you basically tell the system, you pay a price for using a vector that has a high L1 norm. And again, this works in the sense that if you train a system like this, if you train the W matrix so that you get low energy. So again, here you have to do inference, right? You have to, if I give you a Y, you have to find a Z that minimizes this energy, okay? So let's call it Z star, which is the argmin of E of Y and Z. Okay, so you find a Z that minimizes the energy. And then you do one step of gradient descent with respect to W to update the Ws. There's a few tricks you have to apply to prevent W from blowing up, but that's kind of a bit of a detail. This works really well. If you train sparse coding to represent image patches, for example, the columns of W end up being beautiful Gabor filters and things like this, which is what you would expect. So those are two examples of latent variable self-supervised learning, if you want. There is no X in this case because it's completely unsupervised, it's not conditional. But basically the question I'm working on right now is how you make a learning system with an architecture similar to the one you see on the left with a good regularization for the latent variable that allows the system to make multiple predictions, but without degenerating and without necessitating a contrastive phase where you push up the energy of negative samples. And you know, that's where I'm at. I mean, I have a few results on various things, but it's less interesting than the whole principle, if you want.
Oh, that's very exciting. I wonder when we can use that. You know, there are a lot of students here think about how to use this for NLP speech. So right. yeah, it's very interesting. We'll probably come back to more questions. So I want to, given the time, I want to ask you one more question and then open the floor for the audience to ask questions via Q&A. Sure. Is that okay?
Yeah.
So my question, yeah, can I spotlight you? Yeah, okay.
Yeah.
I'm gonna, okay. So my question is this, it's a little bit higher level now. So we have gone through the past and the future, present. So you are one of the co-founders of Partnership on AI. This is an NGO that's working on that concerns itself on beneficial AI to benefit, you know, the ethics of AI, from technical solutions to governance of AI. So we are HKUST is also, I think we're the first Chinese member or partner in the partnership. So I would like to ask you the following. So given, so many AI applications today, and given that in the current crisis, the COVID-19 crisis, so what are your thoughts on how AI can be used to benefit the society? And what are your thoughts on how AI can be used to help fight the pandemic of COVID-19? And given that you also work for Facebook, I'm sure that a lot of people have questions, burning questions about, the view on, data security, and, what are the ethics of, social media, data mining, and so on. All that, I think it's like a very big concern. And today we know some people, some countries are using contact tracing programs to trace, infected people and their contacts in order to contain the epidemic. And this is also kind of, controversial. So could you share your thoughts on, what are the AI technology you believe it can help benefit mankind and humankind, and also to fight the pandemic, but also what are the ethical issues that you think there are, and what possible, your thoughts on, your takes on the whole thing?
Right. So there's a number of different things that I know people are working on, specifically for the current pandemic. But those are generally derived from projects that people were working on previously for either other problems or similar problems, right? So one, which is not completely obvious, is predicting the dissemination of the pandemic, like predicting, how many people will, become infected in a particular area over the next few days or weeks. And this could be very useful for local government to do resource allocation, hospitals, ventilators, masks, whatever. Kind of redeploying healthcare professionals, etc. So there's actually a project precisely on this at Facebook, and that project was put in touch with the various local governments in the US, particularly in New Jersey and New York and California. And this is the model that was built. It was built by mostly by a researcher at Facebook called Max Nicol. It's using something called multidimensional hog process. I don't know if you ever heard of this. And it uses data, so aggregated mobility data. So it knows, for example, that there's a lot of people from this county who are friends with people in that county. It knows roughly, the statistics of how many people travel from one county to another. This is, coarse-grained aggregated data. And it also has historical data of how many cases there are in each county. And from this, you can kind of make a prediction as to like how the disease will progress. That's kind of useful. But it doesn't cure the disease, right? It's good to know in advance what's going to happen, but it's not going to control the pandemic. It's going to maybe allow you to kind of take measures at the right time, which the US has been
resources, maybe medical staff, and allocate resources, right?
Yeah, resource allocation, exactly. And just tell people how, like it helps to be able to make this kind of prediction, to convince people to stay home or wear masks, or in the West it's very unusual for people to wear masks. Convincing them to do this is very hard. So I mean, people kind of do it now, at least in densely populated areas like New York and New Jersey, but not so much in rural areas. And other areas. So this data can help. So that's one possibility. There's another one which is pretty obvious, which is basically using modern computer vision method for analyzing X-ray images of lungs, either CT scans or regular X-ray. So what would be interesting would be to kind of train a system to kind of diagnose from X-rays with the same level of reliability that human radiologists have by looking at CT scans. So basically, it's very difficult to, from what I'm told, okay, it's very difficult to diagnose COVID-19 infection or, from a regular X-ray. It's much easier from a CT scan. But perhaps it's possible that, you know, neural nets might be able to do it better. So if you have both a CT scan, if you have a CT scan, you can generate a synthetic X-ray. You can produce an image that looks like an X-ray, right? And maybe you can train a neural net to generate the CT scan from the X-ray, something like that, right? So there are various projects along those lines at Facebook. And those are people who do computer vision, but, you know, I haven't done much X-ray. There was a project in radiology at, there is still at Facebook on accelerating MRI data collection. It's called Fast MRI. It's actually an open competition. Whoever is interested in your class can actually participate.
Yeah.
And, you know, a couple other projects along those lines. So certainly in imaging, there's a lot of possibilities. There's another project at Facebook, but various people are working on similar things, which is sort of trying to use causal inference to figure out what are the factors that affect the gravity of an infection, either for an individual or at the population level. So for example, there's a big question now, which is that it seems that countries that vaccinate people using the BCG against tuberculosis seem to have fewer bad cases of COVID-19 than countries that don't vaccinate people with BCG. Okay? And it's not just BCG, it's certain strains of BCG. So, you know, for example, France, you know, I was vaccinated with BCG when I was a kid, but in France, they use a particular strain, which apparently is not very efficient against COVID-19.
Oh, really?
Right, which, in fact, apparently the most efficient ones are the ones that are used in, you know, in Africa and Southeast Asia. So I don't know what.
Hong Kong, I heard we use them. I heard.
Which one? Pardon?
In Hong Kong, I heard, you know, in the East Asian countries, we apparently have them. And maybe that's.
Yeah, I'm not sure what type of BCG is used in Hong Kong, but I think it's the one that actually works against COVID-19.
Yeah, apparently works.
So,
yeah.
So, but it's a bit of a mystery, right? There is no real proof for this. It's more like a hunch. So, so the question is, you know, can you use causal inference?
Yeah.
To kind of establish those links. And there's a bunch of people at Facebook who are really interested in causal inference. People like Léon Bottou, whom I mentioned before, Alex Pesakovic, David Lopez-Paz in Paris, and, you know, people like that. And those kind of causal inference could also be used to design sort of experimental protocols for testing new drugs. And then there is the last thing, which is, can we use deep learning to design new drugs? Say monoclonal antibodies, right? And so there's also a project like this.
Yeah, I think that, you know, for when you talk about diagnosis, because we here at UST, we also work on and collaborate with some collaborating groups on using speech to diagnose, you know, we've heard people working on speech processing to diagnose coughing and breathing, and also language, we, you know, to mine scientific papers, you know, sort of keep question answering answer. These are all using deep learning. So when you mentioned the radiology, you know, image, we can perhaps think of a way to combine, you know, the multiple diagnosis tools for doctors to do a better job, because not a single tool is 100% accurate and there's false negatives and so on. Maybe they can combine them. And I think it's more than ever before, we need to collaborate, right? People and groups can work together, and they're like sort of open source. We are all open sourcing all these programs. Yeah, and
no, I mean, I think it's great because people tend to. I mean, I've seen people who are pretty competitive actually kind of collaborate more because you know, they understand the urgency of the problem. Even in people in companies that are like pharmaceutical companies who would normally never speak to each other because they're so secretive, they're kind of, you know, opening up their IP because they say we need to solve that problem. And
the Google, Apple just you know, collaborated for some programs for.
Right. Yeah, so you were asking about privacy. Okay, so I have to make a terrible confession, which is I know absolutely nothing about computer security, privacy, and cryptography. Okay, this is an area of
It's not
information.
AI.
And
Okay.
I know absolutely nothing about. No, but I mean, a lot of people have a personal interest in it, even
Yeah.
even if they're not working on it. I actually don't know anything about it, so this is not something I'm kind of interested in. But um, what people are working on is ways to identify whether two persons have been in the same place at the same time in a privacy protecting manner. And the way to do this is you get two smartphones to talk to each other through Bluetooth, only if they are nearby, and they exchange random codes. And so the codes don't identify you, but you know, you get the codes from whoever is near you. And then if you get diagnosed with the virus, you can tell your smartphone to upload your codes. So the codes don't identify you, but then anyone can look at the list of all the codes if it contains the codes that they emitted. Okay, so now they know if they've been in contact with someone who's been infected without knowing who it was. You don't know who it is. They don't know who it is, but they know they've been in contact with someone who's been infected. That's the basic idea. So there's an open source project out of Europe that kind of uses this principle. And then the sort of Apple Google collaboration is kind of along similar lines. And the reason, so you don't see, the reason why you see Apple and Google in this project is because Google controls Android and Apple controls iOS. And so between the two of them, they basically control every mobile device. Mm-hmm. You won't see Facebook there because, you know, Facebook doesn't have any entry there, doesn't have any control, right? I mean, if you run Facebook, of course, that wouldn't work in China, but if you run Facebook, only about half of the population in most countries actually have Facebook installed. And among those, only a small proportion have location information activated. So for most people, Facebook has no idea where you are. It's only a small proportion of the population that have location tracking turned on. And so it wouldn't be very efficient. Like you wouldn't be able to really tell if people are in contact with each other. But aggregated data, like social connection data, would be useful, I think, yeah.
Okay. So can you just make one final comment on, and then we move on to Q&A with the audience. So one final comment is that what do you think of, so what are the efforts that you can tell us from Facebook on combating fake news? For example, there's a lot of false information, disinformation, even about COVID-19 today. And they can cause harm, actually. So can you tell us what Facebook is doing to using AI? I mean, of course.
Right. Okay, so there are certain things using AI, NLP that are possible to do and, you know, must be done and are relatively easy to do. So you want to detect, you know, violence or pornography in a photo, you know, computer vision works, right? You want, you know, people can put things for sale on Facebook, and you don't want them to sell guns, for example, or so you can detect, you know, whether that's happening. You know, people use Facebook Live to kind of, you know, post, you know, live videos, and sometimes people do horrible things in those live videos, like they kill someone or they kill themselves. You don't want to be showing this to everyone. And it's very difficult because you don't have many positive samples of that, right? And so there was a story a couple of years ago or something, this guy in Christchurch in New Zealand who, you know, ran into a mosque and, you know, killed 50 people. And the Facebook automated system didn't pick that up right away. And, you know, because there's basically nothing to see in this video. You hear a gunshot, you hear people screaming, but you don't see much. And there is a lot of legitimate videos where that happens, where there are videos from video games or from Hollywood movies. And so how do you make the difference? I mean, it's very hard, right? So that's probably one of those domains where things like self-supervised learning might help eventually, because the number of examples, training samples is thankfully very small. And then in NLP, you can do things like detect hate speech relatively easily. I mean, it's very far from perfect. And you can't really kind of set the threshold of detection of hate speech very low because people get really upset when you take down their content. And so, below a certain threshold, it becomes kind of censorship a little bit. So you had to set the threshold pretty high, but then, some things that are obviously hate speech actually go through. So you can never do this perfectly. Now for fake news, it's much harder for various reasons. First of all, there's a lot of fake news that's completely legitimate, right? You tell a story to a friend, and it's a fictional story, but it's fine. Okay, is it fake news? Is it just fiction? As long as, even if it's fake news, like what if it is satire or irony? You say something that's false, but it's false. You're kind of making a joke. Or it's just two people, within a family or a group kind of talking to each other. Why would you take it down? It's not public. So what you want to do is take down fake news that has a lot of impact, that comes from organisms that are followed a lot. But then you upset a lot of people when you take them down. And it has to be a combination of human intervention and, some sort of AI flagging. But to flag fake news is basically right now consists in flagging unreliable sources rather than actually flagging the news itself.
Exactly.
Okay. It might come in a few years that we'll be able to tell if something is inconsistent with, some known fact, but right now it's not possible. And it may not even be desirable because, the truth of a news is very often in the eye of the beholder.
So our group is going to launch this sort of a Q&A engine that queries scientific publications around coronavirus. So one way we could do, there's an idea and we're working on, which is that since we can Q&A this kind of scientific evidence, and if the system can return some kind of confidence score and tell us it's not there. So if you ask some question and it cannot be found in scientific publications, the very least we could do is that we have not found any scientific evidence on it. So
right. And you could probably use a combination of natural language inference and like information retrieval, right?
Right. So this is what we're doing. And then another issue is that when people ask questions, so medical professionals and researchers will ask very intelligent questions, right? A lot of the fake news questions are just kind of, sometimes we know it's fake because it just look dumb, like does drinking bleach cure the virus, right? But how do you translate that into the query that can be used to query the scientific papers? That's also a very challenging natural language processing problem. So this is an advertisement for students at UST who want to participate in this effort. Please talk to us and we can work on this together. So thank you so much, Yann, for wonderful. It's really exciting and wonderful talk. Actually, it's a fireside chat, but it's very, very substantial. Given the time, I would like to let the audience members to ask questions through the chat. So you can ask questions via Q&A, and I can see them. Then I'll tell Yann. So do I need to do anything to open it, or?
I can see them too. So.
You can see. Okay.
Yeah, but you can pick the question for me.
Yeah. I don't. Do you see them?
I see.
Oh, here. It's not chat. Sorry. Okay. Okay. So there are 4 questions. We have time to answer them all. Do you want to start from the first one?
Okay. First one. In terms of AI applications to help fighting COVID-19 pandemic, how good are room for improvement in information sharing?
How to keep a good balance with data privacy, information security?
Yeah, well, that's a very broad question. I don't think there is any simple answer to that question, and I'm probably not the best person to answer it.
Yeah.
Because as I told you, I don't know anything about security. I mean, I know something about privacy, but that's a different story. But I think people are very inventive. So those ideas of doing contact tracing without revealing the name of anyone to anyone, I think is really interesting. Most countries that have done tracing use mobile phone data, and generally that data is kind of centralized by the government. There are certain countries like the US where that would be completely unacceptable. In some countries like in Europe, It would not be entirely impossible, but it would probably violate some of the laws. So, doing it in a sort of privacy preserving way is very interesting, and entirely possible. I mean, people just, come up with good solutions for this. There's something in the context of machine learning that I find quite interesting also, federated learning. Distributed learning on multiple servers.
Distributed, yes.
Out of which knows really the complete data. And then there is something very new, which is not completely practical yet, called holomorphic encryption. So this is the idea that you can take a piece of data, encode it in some ways that you cannot recover the original data, but there is, if you were to do an operation on the original data, like multiplication or addition, you can do it in the encrypted domain, okay? So you encrypt the two data, then you do an operation between them, and then when you decrypt, what you get is the product of the original pieces of data, or the sum, or whatever. So you can imagine computing neural nets, right, from encrypted data. But right now it's so expensive that it's not really practical.
Oh, that's very interesting. Actually, I want to choose the last question for you to answer first. It's I think a lot of students have that question. It says, my question is, would you share some traits that you found beneficial for one to come up with a brilliant idea, like you come up with CNN? In other words, how did you maximize your chance to have those aha moments besides luck?
I wish I knew. I don't know. I mean, I'm sort of a, I think there's many different styles of research, and all of them are useful. So I have a particular style, which is that I try to kind of simplify the context, the concepts as much as possible to get to the core of really what matters. And it's basically, perhaps reflected a little bit in what I explained about energy-based models. One of the things I kind of said without saying it is that, everybody uses probabilistic modeling. And I think in some cases it's just wrong. It's not wrong because it's mathematically wrong. It's wrong because it gives you the wrong answer, the wrong behavior. And to be able to challenge a set of techniques that are widely accepted, you need to be either foolish or really sure what you're advancing, or sufficiently old and reputable so that your reputation will not be damaged by it, okay? Or at least not too much. But that, that requires a little bit of chutzpah, as they say in New York, okay? I'm not sure everybody in Hong Kong knows what that means. But it's, a little bit of self-assurance, if you want. I mean, if you really believe something is true, you should pursue it. Something is good eventually. Now, the second thing is, you don't want to be shooting. I mean, you have kind of a trade-off to choose when you do research, right? You can choose to do research projects that are pretty safe. You're pretty confident that you're going to get good results. It may not be sort of earth-shattering, revolutionary result, but it's going to make some progress, and it's something you can build on. You can add a publication to your CV, and maybe that will help you get a job. Okay, but often if you are beginning your PhD or something like this, you're better off shooting for a more ambitious result. So something that might require a couple of years before you get a result, but would be kind of more meaningful if you want. Okay, not as incremental. And the way to kind of ask that question is to kind of look at what people do and say, like, in what everything people do is, kind of think that there is something wrong with all the approaches. Okay, that sounds incredibly arrogant, and it is sometimes, but sometimes it's something very obvious, right? So let me take the example of convolutional nets. All right, the first obvious thing to me when I started working I was still an undergrad. Okay, I didn't have anybody to mentor me, but it's something that was completely obvious to me, which is that we were not going to be able to build intelligent machines without allowing them to learn. I thought really learning was completely essential to AI, and I could not imagine that we'd be able to just conceive an intelligent machine from scratch. Learning was really inseparable from intelligence, in my opinion. Okay, so now you establish this for yourself. You're really sure of that, okay? Now you look at the literature and you realize, if you were like me in the early 80s, nobody is working on learning. There's no such thing as machine learning. The only literature I could find was from the 60s. And okay, and then, you know, the other obvious idea is that why don't we get inspiration from the brain, because the brain is a good example of a machine that can learn. So I started looking at the literature on, you know, I discovered neural nets, right? And again, I discovered that nobody was working on this in the early 80s. Everybody had dropped the entire topic in the late 60s, early 70s, except for a few Japanese researchers, actually. So that's kind of the second obvious thing. And then the third obvious thing is, why don't we get inspirations for the visual cortex? And then there is this idea that you look at the classical pattern recognition literature, which I did when I was an undergrad, and it all works by extracting features, right? You design a feature set by hand, and then you plug a classifier, a tree, a linear classifier, a nearest neighbor, you know, whatever, right? That was called statistical pattern recognition. And you immediately realize that the brain doesn't do this, right? The feature extraction in the brain is also neurons. It's part of the same process that does classification. And so you say, you know, if you believe in learning, the features have to be learned. Okay, so start from the necessity of learning, the kind of obvious idea that you need to train the system completely end to end so it can learn the features and the classifier at the same time, and then get inspiration from the brain and the visual cortex, and you get convolutional nets.
Yeah.
And once you get this idea, it's completely obvious to you. You know, I mean, you can even imagine that people think about other things, right? Because it becomes completely obvious. So if you have an idea like this that looks fairly simple and is obvious to you, but you have a hard time explaining to others, that means you are probably onto something, okay? And it took 20 years to convince people this was a good idea. So even though it was completely obvious to me.
There's a lot of intuition, persistence, experience, looking at what other people are doing.
And also simplicity, so conceptual simplicity. So
elegance.
Very often in academia, we are driven to kind of come up with really complex models because the mathematics is cute or impressive. We're going to impress our friends and our colleagues.
Easier to publish.
You know, right? Sophisticated mathematics. So for example, there's a very interesting story in the late 90s, early 2000s. People like me and Léon Bottou had been working with stochastic gradient descent for a long time. And stochastic gradient descent is the simplest program you can write. It's 3 lines, right? You compute the gradient, you do gradient minus, you do parameter minus gradient with some step size, you decrease the step size. It's trivial, right? The math to prove the convergence is very complicated. Léon actually wrote the definitive review paper on this. But then at the time, people were interested in, you know, convex methods, supervector machines, kernel machines, and they were using semi-definite programming, you know, primary dual methods, you know, all kinds of complicated stuff where you can write pages of cute math. It turns out all that stuff is much, much slower than stochastic gradient descent. And, you know, Léon kept telling people about this and they just did not believe him. And so he ended up just writing a short C program, which he put on his website, and he said, run this, okay? This is, you know, the best SVM stuff that you can come up with using non-stochastic gradient. This is stochastic gradient, that's for SVM. Here's the same thing for conditional random field. Okay, here's the same thing for logistic regression. And you just put the code online and said, like, just run this, right? It's 1,000 times faster. Even that was not sufficient. He had to write a paper with a theory that showed that, you know, stochastic gradient was a good thing. So people get prisoners, you know, are kind of imprisoned by their own ideas. It's very difficult to kind of change their mind. Yeah.
So perhaps you can choose 1 or 2 of the questions before we end the whole webinar. You can choose.
Okay, I like the first one. Graph neural nets can be used to solve some problems that convolutional neural nets or recurrent neural nets cannot. Well, yes and no, in the sense that there is such a thing as graph convolutional neural net. So those concepts are not mutually exclusive. You can have a graph neural net that is also convolutional. But I'm a big believer in graph neural nets. I think it's a very, very cool domain. I wrote some of the early papers on it, and I'm not actively working on it right now, but I think it's a very exciting field. So there's a lot of things, you know, it's basically domains where the data comes to you not in the form of an array, but in the form of a function on a graph, and that graph might be irregular. It might change from example to example. And so you have to wear representing a neural net so that it can take data from a sort of a graph whose structure changes from sample to sample. And for doing things like representing chemical molecules, representing the local graph in a social network, and all kinds of other things, even images. So for example, imagine you have one of those spherical cameras that takes a spherical 360 image. Your image is not on a Euclidean grid, it's on a sphere. How do you run a convolutional net on a sphere? How do you define a convolution on a sphere? Turns out you can. It's relatively easy. You do it in polar coordinates, but it's not obvious, right? And so those are things that graph neural nets can do. And I think it's a great topic. If you're looking for a topic for a thesis, a master's thesis, or PhD thesis, that's a great topic to work on.
That's great.
Right.
There's another question from Genta, my student actually, on the interpretability of neural net. Do you have any recent findings how to understand, interpret the learned weights of neural network models?
Okay.
Depending on the application, right?
I have a very unorthodox set of opinions about explainability and interpretability. I do not believe this is useful at all. Okay. And this is very unorthodox. And I'm used to having opinions that other people don't have, so it's okay. But I think, okay, I've been in the situation a number of times talking to people who wanted to use machine learning, and you sit down with them and they explain their problem to you, and they tell you, they look at you in the eyes, and they say, it's very, very important that the model be interpretable. It's very, very important that we can generate explanations for the decisions. Okay, and then you go away and you work on the problem for a while, and you build two models. One is a linear regression or logistic regression. Very easy, it's not a black box, it's got weights. And the other one is some gigantic neural net that is really complex inside. But the neural net works better. Okay, so you go back to the person you talk to, like give you the problem, the customer. You tell them, I have those two models. One of them is explainable. Doesn't work very well. The other one is not explainable, but it works much better. Which one do you pick? Every single time, the person will take the second one. Every single time. Which means it's the same person that just a minute before told you it's very important that the model be explainable. But in fact, it's not. Never. Okay? They just want a system that works. And so the question is, how do you prove that it works? That's a real question. And the example I use very, very often is, there's a drug that has been used for decades to treat bipolar disorder. It's called lithium. So lithium is not even a molecule, it's an atom. Okay. And you give lithium to people who have bipolar disorder, and it seems to kind of moderate the symptoms. For some people, it works really well. Nobody has any idea how it works. It's a very, very complex set of phenomena, interactions in the brain. Like basically, people don't understand how it works. Until the 1970s, the drug that has historically been the most used in all of humanity, aspirin, until the 1970s, we had no idea how it worked either. It worked, just didn't know how. So it's not because you don't have an explanation that you can't use something, okay? But if you don't have an explanation, you have to have very, very, very good testing. So basically, you have to build a ROC curve, or precision recall, selectivity, whatever they call it in medicine, right? They have a name for it. It's a different way of normalizing the ROC curve. Otherwise, you have to have an explanation, sometimes both. Now, there are situations where, for legal reasons, it's required to have an explanation, like legal decisions. But I don't think you would want to use machine learning for legal decisions anyway.
No, yeah.
So, okay, that's the first point. Second point is a neural net is not a black box. You can do sensitivity analysis, so you use some giant neural net to decide whether to give a mortgage to someone, like a loan or something, right? And what the person wants to know is, like, why did you turn me down? And the best kind of answer you can give them is, well, if your income was, $20 more per month, maybe we would have given it to you. And you can do this with a neural net. You can do sensitivity analysis. You can minimally change the input to flip the answer. And that's perfectly good explanation to give to people.
Thank you. Perhaps one last question, and
okay.
we'll end the session. You pick one.
Okay. There's a question about science fiction.
Yeah.
There's a question about causal inference. Yeah, causal inference is a really important problem. You know, I have my friend Yobotu that I mentioned, and David Lopez Paz, Bernard Cholkov, they're really interested in causal inference because they think that you know, it's a necessary step to use samples in a more efficient way than assuming independence of the samples. If you can establish causal dependencies within the thing, it's connected with the whole argument I gave about self-supervised learning, right?
Mm-hmm.
If you can predict some variables from others, you might be able to establish causal relationships, which means you have some sort of internal structure of the input, and it might allow you to generalize better, right? It's also an interesting problem in itself.
Mm-hmm.
Let's see. Oh, impact on computer architecture. Yeah, I actually gave a keynote. So this is the impact of machine learning on computer architecture. I gave a keynote at the ISSCC conference, the solid state circuit conference last year in it was early 2019, and my keynote was you know, how hardware influences research in AI and machine learning, and vice versa.
Mm-hmm.
What I try to tell people, these were hardware people, it's clear that AI and deep learning already has had a big impact on computer architecture, right? So now you have, you know, special instructions in a lot of like new processors coming out that basically are designed for neural nets. New cell phones come up with have neural net accelerators on them. There's a bunch of companies, you know, in China, Taiwan, and other places that produce very, very cheap neural net accelerators, you know, that consume very low power. And those things are going to be everywhere within a few years, mostly for mobile application in smartphones, but also for things like virtual reality and augmented reality glasses, for example. So those would require like very, very low power consumption chips that can run fairly complicated neural nets that can do tracking and you know, gaze tracking for eyes and things like that, and SLAM and things like this. So that's actually a huge set of projects. And of course, for you know, the sort of different types of machines, there's the machine you use for high power training. So basically right now it's NVIDIA GPUs or Google TPUs. That's all there is. Then there is kind of run-of-the-mill production learning. You know, you don't need to have enormous GPUs. You can run in 16 bits. And for that, you know, there might be kind of specialized hardware that might be appropriate for this. And, you know, a number of different companies are working on this kind of hardware. Then there is inference in data centers. So your Facebook, people upload billions of photos on Facebook every day. Every single one of those photos has to go to half a dozen different neural nets to be filtered and recognized and indexed and whatever. And you need to run those neural nets within 2 seconds. You can do this on Intel processors, but it's kind of inefficient, right? So it might be good to have specialized architectures to do this, but they will still be in data centers. And then there is processors you want to have in cars and, you know, automated lawnmowers and stuff like that. And then there is low power processors in smartphones and smart cameras and toys and things like this. And then like super low power things for augmented reality glasses and cheap toys and that kind of stuff. So there's a whole spectrum, and it, I think it's actually has revived the excitement in the hardware community, which, you know, there was not like, I mean, I think it's, you know, you see a lot of papers coming out on this topic and a lot of people excited about it, and a lot of conferences where, you know, new startups, you know, there's like tons of new startups on the topic that are starting, which means, you know, there's opportunities and it's exciting. I'm excited about it. I used to be a hardware guy a long time ago.
Really? Well, with that, I think we are going to conclude today's webinar and the fireside chat with Yann LeCun, Professor Yann LeCun. I certainly enjoyed this very much, so I hope everybody enjoyed it. And there's a lot of content. We will be uploading the video later on for the community. And so thank you so much, Yann. So
sounds good. Well, thanks for inviting me. Sorry I can't be here in person.
I know.
I've meant to come to Hong Kong for a while, but
well, when this is all over, like the Queen said, we shall meet again.
Yes.
All right. So thank you so much, Yann. Thank you, everybody, for attending.
Thank you, everyone. Have a good day, everyone.
Have a good
one. Thank you. Thank you.
Thank you. Good night. Yeah.
Good night. Take
Good
care.
Night. And keep safe in New York.
All right.
Bye.
You too.
Bye.
Bye-bye.